In 4.5, we're going to talk about the graphs of cosine and sine. So, ideally, a graph is just a bunch of ordered pairs that are so next to each other that it seems like they make a line, right? So, you have a function, and you input the x value and you get the y value out. In our case, we have the function sine, cosine, and tangent, and as we know it, they all have some kind of input and some kind of output, right? And that's what we're plotting in the x-y axis, and then whatever shape we get, it's going to be the graph of our functions. So just a quick review, x is the input and its format is an angle in this situation, right? So whatever you're plugging into this trig functions is going to be an angle either in degrees or radians, and I think we're going to be working a lot in radians. So then the output y is a ratio of the sides of a triangle, right? That's the definition for sine, cosine, and tangent, which are some of the most popular functions that we talk about. Okay, the first one we'll talk about is sine, and the idea is that the first definition we learn is that sine of an angle equals y, and that y refers to the order pair here. So if you say sine of 0 or 0 degrees or 0 radians, is going to be the value y of that order pair. So in this case it is 0, like we're showing here. So if you plug in a 0 and you get back a 0, then the point that we're going to plot is going to be 0, 0. Makes sense. Then we have another example like pi over 6, which is 1/2. So this is the order pair we'll use. Pi over 2 equals 1. This is the order pair that we're going to use for graphing. Even though we can figure out that sine of 120 degrees is square root of 3 over 2, we're not going to use degrees to plot. Okay, we're going to use radians for the most part. Okay, then for cosine, the first definition that we learned was that cosine is the x value, right? In some sense, that's what we said, but it is the x value of the order pair that is on the unit circle, right? So if I say cosine of 0, well, that point is located at 1, 0, and that 1 corresponds to the cosine function, like we're showing here. We can also say, what is cosine of pi over 6? And then we get the number square root of 3 over 2. And just like before, we said, well, we could plug in degrees and still get an answer, but we're not going to use degrees when trying to graph these trig functions. And just as a reminder, this is the input and that is the output, right? And that's what makes an order pair. Okay, how are we going to create the function sine, or the graph of the function sine? Is going to be by using some of the order pairs from the unit circle that we know. So x being the inputs, so if we were plugging 0, sine at 0 is 0. Sine at pi over 6 is 1/2. Sine at pi over 3 is the square root of 3 over 2, and so on, right? So what we have left to do is just plug in those values and see what we get. So 0, 0 is right here. Then pi over 6 is 1/2. Pi over 3 is square root of 3 over 2. 1/2, when you plug it in, gives you 1, and so on, right? So you get the idea that these values go all the way up to +1, and then they come back down, right? At 7 pi over 6, we get -1/2. So right here, 4 pi over 3, we get negative square root of 3 over 2, and then 3 pi over 2 gives us -1. And then we start coming back up. Okay, so let's see if we can make this kind of curvy, since it's supposed to be a little curvy wave, not so sharp. Okay, so all we have to do is connect the points together and this is going to give us the shape of the function sine, and it's supposed to be a smooth curve, not so sharp like mine, obviously because it's by hand. So ideally we're going to get this graph, right? And it's a curve, it's a wave, but you get the idea here, right? The next thing that we want to do, or at least understand this shape, right? It starts at 0, 0, it goes up, comes back down, and it goes back up. Notice how there are 1, 2, and 3 x-intercepts. That's going to be a good characteristic to remember about sine. Then let's talk about the function cosine. Same as before, right? Here are the x values that we got from the unit circle, and if we plug them into the function cosine, or we're evaluating the function cosine at these values of x, these are the corresponding values that we get. So if we were to graph this at 0, the function equals 1. At pi over 6, we get square root of 3 over 2. At pi over 3, we get 1/2. At 2 pi over 3, we start going down below. Then 5 pi over 6, we get the negative square root of 3 over 2. At pi, we get a -1. And it's the same thing as before, right? We start creating this pattern of up and down, and then up again kind of thing. 3 pi over 2, we are at 0, then 1/2. Oops, that's kind of low, it seems. Then 11 pi over 6 is square root of 3 over 2, somewhere over here. And then pi over 2 is this right here, right? So we're going to get something, if we connect all the dots, definitely going to be a very, very sharp graph. And I don't mean sharp as in good. It's supposed to be very, very smooth, and this is looking very, very sharp, and what we want is something like this, right? I see some resemblance, but it's very, very sharp, right? It's not the best graph, but it gives you the idea. Okay. some characteristics of the function sine and cosine. So on the left, like I mentioned, this is the graph of sine, and notice how it starts at 0, 0 and then goes back up. And on the right graph we have the function cosine. So one important characteristic of both actually is what they have in common is that the domain is from negative infinity all the way up to positive infinity. That means that you're allowed to plug in any value of x or any input that goes from negative infinity all the way up to positive infinity. Meaning, right, that there is a graph over every value of x in both cases. The range for both functions is from -1 including all the way up to 1 including. So the range, the output, the lowest value that you could get is -1, the highest value that you can get is +1, and that happens for both sine and cosine. Cool. We notice the period is 2 pi for both, right? And what that means is that it's the length, or I guess, yeah, you can call it the length, or the values of x, that it takes it for it to go one full cycle, or once around the whole unit circle, right? So that's why in the graph that I did, I only graphed one cycle. So it was this, right? The idea is that the function goes on forever to the right, and it goes on forever to the left, and in the same shape just follows, right? And same with cosine. The only graph, or the only piece that I did was just one cycle, or the period, right? But it's the idea that it goes on forever to the left and it goes on forever to the right. Now, some things that are very specific to cosine, for example, is that it's an even function. What it means is that if you plug in a negative value, that's going to be equal to that of a positive value. So what does that mean? Here on the red I have some negative x value, and here's some positive x value. Notice how I plug them in and they map to the same output. I plug in the positive x and it maps to the same output. Okay, and notice how there is a reflection over the y-axis. Well, that's another characteristic of even functions. Okay, and if you wanted to write cosine in terms of sine, cosine is pretty much sine function, but it's been shifted to the left or to the right pi over 2 units. So think of this graph, if you move this to the right pi over 2 units, well, it just becomes the sine graph. Okay, also sine is an odd function. What does that mean? Well, if you plug in negative sine, it is going to be the same thing as a negative times sine of the positive. Well, I'm showing you that here, right? Here is some negative x value, and here's some positive x value. Well, this is the output that you get for the negative x. And this right here is the output that you get for the positive x. But if you were to make it negative, it flips back down to this, right? And that's what we're showing here in this explanation. Another thing is that there is a symmetry, and it happens to be about the origin, meaning that this point should be reflected diagonally, and it ends up right here. If you wanted to write sine in terms of cosine, you can just say that sine is the same thing as cosine of whatever input plus 2 pi, right? What it's saying is that if you have the function sine and you shift it to the left pi over 2 units, notice how it would start right here, and that is the function cosine. The next thing that I want to do is do some kind of general analysis on the function sine and cosine. And what I propose is that the functions that we analyze more generally is just the simplified version, which is sine of x and cosine of x. Right? It's good to be aware that there could be other numbers that are involved in the function, right? So here we have a times sine. There could be a b, or a number, times x, plus or minus some number c, and then outside of the parentheses, plus or minus some number d. And that can happen again even with the function cosine, right? So a, b, c, and d are just numbers. They can be any real number, right? And then when they're present, they should be seen or understood as some kind of transformation, right? They're having some effect on the function itself, and it's changing the way it looks compared to the parent function, right? But we can look at more specifically what do a, b, c, and d do. Okay, so a good example here is the plain parent function y equals sine of x, and you have a, b, c, and d, and here I am explaining what they do. So a tells you the amplitude of the graph. The amplitude of the graph is going to be this value from here all the way up to here. You know, how tall is the wave? That's the amplitude. So notice how that measurement is going to be the same as here, right? It's not all the way from the top to all the way on the bottom. That's not how the amplitude is measured. So just be on the lookout for that. B is going to help you determine the period. So the period is going to be one full cycle of the graph, right? So that is a period, and the period for sine is 2 pi, okay? So however long it takes for it to go through one complete up and down of the graph. Then the values c and d are just a little bit more easy to see, and they're just a shift, a transformation of the graph, meaning c and d tell us whether the graph gets pushed around left and right or up and down. Okay, and what I've done is I've graphed another function sine, a variation of the parent graph right below, and notice how they both are lined up and they look a little different, right? So the first thing that we want to understand is perhaps the amplitude. So there's a line down the middle, and the value of a is 1.5. So notice how it goes from 1.5 all the way up to 3. That is my amplitude, right? So 1.5, and I'm going to move it a little bit over here so that it doesn't bother anything else, right? That's the amplitude. Then we talked about the period. So how long does it take for it to go through a full cycle? Meaning, if I start here, for example, how long until it goes back up, down, and to here? Alright, so from here all the way to here is one full period. Notice how it does it very shortly, right? It does it almost, in fact, half of what the other one does, right? This is a period, and if you notice right above, it does it in like half of the amount of the original sine function, okay? So maybe I'll erase this ugly lines here. Okay. Also, my graph has been shifting upwards 1.5 units. So instead of starting from 0, 0, the graph started at 1.5. And then also, this inside here is shifting it. Okay, this got pushed to the right 1.5 units. Okay, so something like this is where it should have started, but then it got pushed to the right a little bit. So it overall is just a variation, a manipulation of the original function. Okay. Here's a guide of to like what you should look for whenever you're graphing a variation of the function. First thing you want to do is identify the amplitude. So the amplitude is the absolute value of the value a. Whatever the value a is, you take the absolute value of it, whether it's positive or negative, you're going to get the amplitude. Then you want to find some values of x, which we're going to call key points. In the case of sine, there are going to be 3 x-intercepts. There's going to be a max point, and there's going to be a min point. So once you have some of those key points, it's just going to be very easy for you to graph the function. In the terms of cosine, you're going to have 2 intercepts, and you're going to have either 2 max points and 1 min, or if it's flipped around, it's going to be 2 minimum points and 1 maximum. Step number 3 will be to plug in the values of x that you found to find to create the corresponding values of y that go with it. Again, connect the points so that creates a smooth curve and it makes one complete cycle. And then in order to get a better graph, you're just going to extend both to the left and to the right in order to get a continuous graph, a more complete graph. Alright, now let's do an example of graphing a sine function. So here we have y equals 3 times sine of 2x minus pi over 2. So this one has all the different things that we mentioned in the previous slide. So let's find the amplitude, and the amplitude is the absolute value of a. So absolute value of 3, right? Then we have, which comes out to be 3. Okay. Then something that's called the phase shift. The phase shift is going to be how much it's moving left or right compared to the original graph. And to find that, we'll do whatever is in parentheses and set it equal to 0 and solve for x. Okay, so that means that the graph has been shifted to the right pi over 4 units. Okay, and if you're kind of looking over here on the right, you already noticed that I've done some marks, right, because that's kind of where I was working on. Then we want to find the period. So the period, you find it by dividing the original period of the graph by the number b, or the letter, whatever value. And so we have 2 pi being divided by 2. Well, that comes out 2 pi. So notice here I have 0, pi, 2 pi. And then here is negative pi, should be a negative. And then negative 2 pi over here. So what's going to happen is that my original graph would start from here, go up to 1, at pi over 2, then come back down, and so on, right? But this one has an amplitude of 3, meaning that it's going to go all the way up to 3, and then go all the way down to negative 3. But it got shifted to the right pi over 4 units. So instead of starting at 0, 0, it's going to start at pi over 4, which is where I have that red dot. Then it's going to go up, come back down, come down, and then come back up, right? And so how do we figure that? Well, since the period is pi, it's gonna go through the full cycle in just a single pi. So let's figure this out, right? So you have pi plus pi over 4. I'm trying to figure out where it ends. So this becomes 4 pi over 4 plus pi over 4, so 5 pi over 4. So if I count, because I broke it into quarters, 1, 2, 3, 4, and 5. So right here is where my whole circle kind of ends. What am I talking about? So my graph is going to look like this. It goes up, and then it comes back down, it crosses, comes back up, and I can kind of stop there if I like. But that's one full cycle of the function we're trying to graph. If I was to keep going, then I'm just going to do something like this. Find the highest, or hit the highest value, start coming back down, cross, come down, and then go back up, right? And so if I was to go on forever, then this is what's going to happen. Right? And if you were doing the original graph, right, which starts at 0, 0, and then it goes up to 1 at pi over 2, then it goes back to 0, at pi it goes down to 1 here, and then it goes down here. So just to give you a perspective of what the original graph looks like, I don't know if you can see it very well. Maybe there's a brighter color. Yep, there's got to be. We'll do it in yellow, because why not? So this is what I'm talking about here. It's the original graph compared to the red line. Okay, can't see it. But But okay, so that's how I figure out the graph of that function, right? By finding the amplitude, the phase shift, and the period. Okay. Next, let's figure out the graph of cosine. So 4 times cosine of 2x minus pi. We have the amplitude be absolute value of 4, so 4. The phase shift is going to be 2x minus pi equals 0, so 2x equals pi, and then x is equals to pi over 2. So this graph has been moved to the right pi over 2 units. Okay, then the period is going to be 2 pi over the b value, which in this case is 2, so it comes out to be pi again. Okay, so the original graph of cosine would have looked something like this, right? Like it goes back up, well it starts, for example, here, it comes back down, it goes back up, but this graph is a little different, right? So the graph has been shifted to pi over 2. So here's one place where we're saying it starts. Then it goes back down and up. So remember, this graph has this shape, right? Something like this, right? It goes up. That's the idea of what we want to do first, at least one cycle, and then go from there. So where else does it cross the x-axis? So from pi over 2 is going to be here at pi over 4. So if we plug in a pi over 4 inside of the parentheses, and let's just show it so that we can see what's going on. This is cosine of 2 times pi over 4. So we have 4 times cosine of pi over 2 minus pi. I'm running out of space, so 4 cosine of negative pi over 2, that's going to be 0, so 4 times 0 is 0, and that's why that value is included. And we look at here, and I'm only going from negative pi to pi, and then in the middle is pi over 2. I broke it up again by quarters, or pi over 4 distances away. So the next value is, what if I plug in 0? Well, if this is 0, then you're evaluating cosine at negative pi, right? What is cosine at negative pi? Is negative 1. Negative 1 times 4 comes out to be negative 4, right? So this is where we are. Right, and so remember, since cosine is a symmetrical graph, then this point has definitely got to be over here on the left side. So we start building our graph. Then we have kind of the shape right here, right? And then it should just go on forever. in both directions, left and right. And that would be the graph of it. Let's do the original. Let me try to get a different color because that yellow didn't work. So if I'm going to graph the original with this scale, it's going to be tough. So, nope, can't even see it. What is going on here? Way better. So at pi over 2, it's 0. Then at pi, it is -1. Okay, so same thing. So that is the graph. The purple would be the function y equals cosine of x. It just looks very weird because it just only goes from -pi to pi. If I had more space, it would look more like the original, but it's going to eventually look like this. Okay, and that is the end for 4.5 and graphing trig functions. Okay, I lied. One last thing before I finish off the lesson here. Just a quick review on all of the graphs, since we're only kind of doing work with sine and cosine, but I don't want you to not know about the graph of tangent and the other functions. So, quick review. Here's the graph of sine, and it has this S shape that starts from 0, 0, and the domain of it is all the real numbers, right? You're allowed to plug in anything because the graph lives over everything that is x. Then the range, it's the numbers of the output, right? So it goes from -1 all the way up to 1 included, and its period is 2 pi, right? From 0 all the way up to 2 pi is how long it takes it to complete one full cycle. Then there's the domain. Well, I'm sorry, I already talked about that. Cosine, sorry. Cosine is this graph. It's very similar to sine, but it's just been shifted, right? So if you start here, you move it to the left, pi over 2, well, you'll end up with the graph of cosine, hence the name, right? They're co-functions of each other. Cosine, right? So, okay. The domain of it is all the real numbers, of course. The range is -1 and 1, and the period is 2 pi. We've talked about cosine and sine a lot, so I'll move on. Tangent, right? Tangent is a function that is a ratio of sine over cosine. So whenever cosine is 0, that's when we have this vertical asymptote, right? So this value here, pi over 2, is what we have this asymptote right here, because as the value of tangent approaches that pi over 2, well, cosine is getting really close to 0, and that's why it goes off to infinity. And then it comes back down right here. So the domain is all the numbers except multiples of pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, That's why it says odd multiples. The range is going to be all real numbers, meaning that any number is possible for an output when you're looking at tangent. Its period is the length it takes it to complete one full cycle. So if you go from -pi over 2 to pi over 2, that is a full period, and it has a length of pi. Okay. Now let's talk about the other functions for a second. So here we have cotangent, and cotangent is just cosine divided by sine, and so its graph is going to be very similar to that of tangent, except it's a little bit shifted to the right and the lines are kind of going in the opposite direction in some way. Very similar. It's going to have all the real numbers as a domain except multiples of pi, right? So 0 pi, 1 pi, 2 pi. Those are the values where there's a vertical asymptote, and then it's going to kind of skip over those. Cosecant, it's related to sine, so it's a ratio of sine. So whenever sine is 0, like at 0, pi, 2 pi, there's a vertical asymptote. And if you remember the graph of sine, it looks something like this. It goes up, touches, comes, crosses the x-axis, comes back down. So there is that relationship of the graph. Okay, and here's the domain of it. It's all the real numbers except multiples of pi. Its range, it goes all the way from negative infinity all the way up to 1. Then there's a union from 1 to infinity, right? So like there is no possible output for the function cosecant between negative 1 and 1, right? There's a big gap in the middle. Its period is 2 pi because it takes 2 pi units for it to go through a full cycle. And here's the function secant, which is just the reciprocal of cosine, and they're related in that way. The graph of it is here, and notice that whenever cosine crosses the x-axis, there's a vertical asymptote here, and the function secant is going to have all the real numbers as a domain except all multiples of pi over 2. Then again, the range of it is from 1 to positive infinity and from negative 1 down to negative infinity, right? And then the period is 2 pi. And that really does sum up section 4.5 now that we've covered different functions as well.